August 14, 1943. New Georgia, Solomon Islands. Private First Class James Morrison, 37th Infantry Division Artillery Forward Observer, crouched in dense jungle vegetation 800 yards from Japanese machine gun positions. His hands gripped the SCR-536 Handie-Talkie radio. He pressed transmit. Static. The Jeep engine 30 yards behind him swamped the signal with electrical interference. He tried again. Nothing but crackle and atmospheric noise. His company was pinned down, taking casualties. Without artillery fire, they would die here. Then his sergeant tapped his shoulder, pointing to a green backpack radio, the SCR-300. "Try this instead," the sergeant said. Morrison wasn't the first American soldier to face death because his radio failed. By August 1943, the communication crisis had been killing American infantrymen for 3 years across 2 oceans. Every battlefield presented the same lethal pattern. When soldiers needed artillery support most desperately, their radios went silent. The problem started with the SCR-536 Handie-Talkie, developed in 1940 by Galvin Manufacturing Corporation and rushed into production by July 1941. The 5-tube AM radio weighed just 5 pounds with batteries, light enough for a single soldier to carry. It operated on amplitude modulation between 3.5 and 6.0 megahertz, with 360 milliwatts of RF output power. The Signal Corps called it adequate. The soldiers carrying it called it something else. The SCR-536's advertised range was 1 mile over land, perhaps 3 miles over water in perfect conditions. But battlefield conditions were never perfect. In practice, the radio's effective range collapsed to a few hundred feet the moment any electrical equipment operated nearby. Vehicle ignitions, generators, tank engines, any spark-producing machinery swamped the AM signal with interference. A jeep starting 30 yards away could render the radio completely useless. Artillery forward observers faced impossible mathematics. Their job required calling fire support from observation posts positioned hundreds or thousands of yards ahead of friendly lines, close enough to spot enemy positions but far enough forward that no wire telephone line could reach them. They needed to transmit coordinates to artillery batteries positioned 3 to 5 miles behind the front lines. The SCR-536's 1-mile maximum range, even under ideal conditions, simply couldn't bridge that gap. When radios failed, commanders reverted to the same communication methods soldiers had used in 1918, messenger runners. Young soldiers sprinted across fire-swept ground carrying handwritten coordinates, dodging machine gun fire and mortar shells, hoping to reach artillery command posts before the enemy repositioned. The runners who survived the journey delivered fire missions 10 to 15 minutes after observers first spotted targets. In jungle fighting, where Japanese positions were dug into dense vegetation and could relocate within minutes, that delay was fatal. The New Georgia campaign, launched June 30, 1943 in the Solomon Islands, turned the communication crisis from a tactical frustration into a strategic emergency. American forces faced deeply entrenched Japanese defenders in jungle terrain so dense that visibility sometimes dropped to less than 10 yards. Artillery coordination became the difference between American infantry breaking through or dying in front of Japanese machine gun positions. But the SCR-536 radios failed constantly in the humid tropical environment. Atmospheric moisture degraded signal quality. Electrical interference from vehicles made transmissions unintelligible. Batteries drained rapidly in the heat. Colonel Francis L. Ankenbrandt, signal officer for U.S. Army Forces South Pacific, watched American casualties mount while his communications equipment failed. Wire telephone lines, strung laboriously through jungle terrain, were cut by artillery fire within hours of being laid. The SCR-536 handheld radios couldn't reach artillery batteries from forward observation posts. Messenger runners took 15 minutes to cross distances that radio signals should traverse in seconds if they survived the journey at all. Technical problem was fundamental to AM radio technology itself. Amplitude modulation encodes voice signals by varying the height, the amplitude of radio waves. Any electrical noise in the environment adds to that amplitude, drowning the original signal. Battlefield environments produced electrical noise constantly, vehicle ignitions firing dozens of times per second, generators producing electromagnetic interference, atmospheric static, from tropical storms, even lightning strikes miles away corrupting transmissions. An AM radio receiver couldn't distinguish between the signal it wanted to hear and the electrical noise surrounding it. Both arrived as variations in amplitude. Both were amplified equally. By August 1943, the mathematics of battlefield communications had become lethal arithmetic. 1 mile radio range, 3 miles to artillery batteries, 15 minutes by messenger runner, Japanese positions relocating every 10 minutes, American infantry pinned down without fire support. The equation had no solution using existing technology. Morrison, crouched in that New Georgia jungle with his company dying around him, represented the end point of that failed arithmetic. The SCR 536 in his hands, state-of-the-art when developed in 1940, was obsolete the moment battlefield conditions differed from laboratory testing. The green backpack radio his sergeant offered, the SCR 300, represented something different. Something impossible, according to the Signal Corps experts who had rejected the technology 3 years earlier. But impossible was better than dead. Spring 1940. The U.S. Army Signal Corps issued a technical requirement that bordered on fantasy: develop a portable battery-powered voice radio for infantry field use with a minimum 3-mile range, immune to battlefield interference, weighing less than 40 pounds. The requirement landed on desks across America's electronics industry. Most engineers read it and understood the implicit message. This was impossible with existing AM radio technology. Daniel E. Noble read the same requirement at Galvin Manufacturing Corporation's Chicago headquarters and saw something different. Noble, director of research for the company that would soon rename itself Motorola, had spent years studying a radio technology the military establishment considered too complex, too experimental, and completely unnecessary for military use: frequency modulation, or FM. The technical principle behind FM represented a fundamentally different approach to encoding voice signals. While AM radio varied the amplitude, the height of radio waves to carry sound, FM radio varied the frequency, the rate of oscillation of the waves themselves. This seemingly minor distinction created a revolutionary advantage. Electrical interference in the environment affected amplitude easily but struggled to corrupt frequency patterns. An FM receiver could lock onto a specific frequency and ignore amplitude variations entirely, filtering out the electrical noise that destroyed AM signals. Noble understood the military's skepticism. FM technology operated at higher frequencies than AM, the very high frequency band, or VHF, between 30 and 300 megahertz. The SCR 300 would operate between 40 and 48 megahertz, roughly 10 times higher than the SCR 536's 3.5 to 6.0 megahertz AM frequency. Higher frequencies required more complex circuitry, more precise engineering, and components that pushed the boundaries of 1940 manufacturing capabilities. The Signal Corps preferred proven AM technology with established suppliers and decades of military experience. But Noble also understood what AM technology could never deliver. An infantry forward observer crouching near a running Jeep engine needed a radio that worked through interference, not a radio that promised adequate performance under laboratory conditions. The Signal Corps requirement wasn't asking for an improved AM radio. It was asking for a radio that behaved differently than AM radios could physically behave. That required different physics. That required FM. In summer 1940, Noble assembled his engineering team at Galvin Manufacturing Corporation's Chicago facilities. Henryk Magnuski would serve as principal RF radio frequency engineer, bringing expertise in high-frequency circuit design. Marion Bond, Lloyd Morris, and Bill Vogel rounded out the core team. They faced a challenge that spanned multiple engineering disciplines: miniaturize FM technology into a backpack portable package, design a power supply that could run 18 vacuum tubes for hours on batteries, create a tuning system simple enough for soldiers under fire to operate, and engineer the entire unit to survive tropical humidity, jungle terrain, and combat conditions. The vacuum tube count alone revealed the complexity gap between AM and FM. The SCR 536 AM handheld radio used 5 tubes. Noble's FM design required 18 tubes to achieve the frequency stability and selectivity necessary for battlefield communications. Those 18 tubes needed power, continuous power, for both transmit and receive functions. The team designed the radio to output just 0.3 watts of RF power, a fraction of what commercial FM stations used, but enough to reach 3 miles with a properly designed antenna and the interference rejection advantages of FM. Power management became critical. The team developed 2 battery options: the BA-70 battery pack, heavier but delivering 20 to 25 hours of operational life, and the BA-80 pack, lighter but providing only 12 to 14 hours. Either battery, combined with the radio components and backpack frame, pushed the total weight above 35 pounds. It was heavy, but it was portable, and it would work through interference that rendered AM radios useless. The tuning system represented another innovation born from battlefield necessity. Most FM radios required precise tuning of both transmitter and receiver independently, a task requiring time and technical skill. Noble's team designed a single tuning control that adjusted both transmitter and receiver simultaneously, keeping them locked on the same frequency. They added automatic frequency control circuitry to maintain clear communication without requiring constant readjustment by the operator. A soldier under fire needed to twist one knob and press one button. The radio would handle the technical complexity. By spring 1941, the team had working prototypes ready for field testing. Andy Affronti Sr., one of the engineers, accompanied Henryk Magnuski for range tests outside Chicago. They separated by 8 miles, more than twice the Army's 3-mile requirement. Affronti keyed his transmitter. "Andy, do you hear me?" Magnuski's voice came back with perfect clarity despite the distance, despite the urban environment with its electrical noise, despite every factor that would have rendered AM radio transmissions unintelligible. The 2 engineers looked at their equipment and understood they had built something that would save thousands of lives. The Signal Corps remained unconvinced. FM was unproven in military service. The radio was heavy. The technology was complex. Established AM radio suppliers offered competing designs using familiar technology. But Noble had the physics on his side, and physics was about to face its final examination at Fort Knox, Kentucky. The spring 1942 acceptance tests would determine whether American infantry would carry FM radios that worked through interference or AM radios that failed when soldiers needed them most. The 8-mile test proved FM worked. Now Noble's team faced a harder challenge, making it small enough, tough enough, and simple enough for a soldier to carry into combat and operate under fire. Between spring 1941 and spring 1942, the Galvin Manufacturing Corporation engineering laboratories in Chicago became the center of a race against time and against physics itself. Henryk Magnuski, the principal RF engineer, confronted the core challenge: fitting 18 vacuum tubes, their associated circuitry, power supplies, and a tuning mechanism into a package small enough for one soldier to carry. Each tube generated heat. Each required precise voltage levels. Each represented a potential failure point in tropical humidity or Arctic cold. The team couldn't reduce the tube count. FM's frequency, stability, and selectivity required every one of those 18 tubes to function correctly. The solution emerged through careful component layout and thermal management. The team divided the radio into two main components: the BC-1000 transceiver unit containing the tubes and circuitry, and the power supply unit housed separately. They designed a backpack frame that positioned the BC-1000 high on the operator's shoulders, allowing body heat to vent away from the tubes while keeping the control panel accessible at shoulder level. The antenna, a crucial element for achieving 3-mile range, folded along the backpack's side when not in use and extended to full height during operation. Weight became a constant negotiation between capability and portability. The BC-1000 transceiver alone weighed approximately 25 pounds. Add the backpack frame, antenna, handset, and connecting cables, and the base radio reached 32 pounds. The BA-80 battery pack added another 6 pounds for a total of 38 pounds. The BA-70, providing longer operational life, pushed total weight even higher. Infantry soldiers already carried rifles, ammunition, rations, canteens, entrenching tools, and personal equipment. Adding 38 pounds of radio equipment tested human endurance. But the alternative was messenger runners dying in machine gun fire or infantry attacks failing without artillery support. The weight was acceptable because the capability was irreplaceable. Marion Bond and Lloyd Morris focused on making every ounce count. They stripped unnecessary components, used lightweight materials where structural strength allowed, and designed the backpack frame to distribute weight across the operator's shoulders and hips. Radio operators would be tired, but they would be alive, and they would be heard. The power supply engineering proved especially demanding. Vacuum tubes require two different voltages: low voltage to heat the cathode filaments and high voltage for the actual signal amplification. The team designed a dynamotor, essentially a motor-driven generator that converted the battery's low DC voltage into the high voltage the tubes needed. The dynamotor became another component requiring careful thermal management, another source of potential mechanical failure, another element that had to survive being dropped, soaked, frozen, and baked in tropical jungles and North African deserts. Bill Vogel concentrated on the tuning system and operator interface. The team designed 41 discrete channels across the 40 to 48 MHz frequency band, each separated by 200 kHz. A selector switch on the control panel allowed operators to quickly change channels, essential when multiple units operated in the same area or when enemy forces attempted to jam transmissions. The transmit-receive switch used a simple push-to-talk button on the handset, familiar to anyone who had used a telephone. Press to talk, release to listen. Simple enough to operate while taking enemy fire. Durability testing revealed problems the laboratory couldn't predict. Early prototypes suffered tuning drift in high humidity. The moisture changed electrical properties of components, causing the radio to slowly shift off its assigned frequency. The team sealed critical components in moisture-resistant housings and added desiccant packets to absorb humidity. Drop tests from truck heights cracked vacuum tube sockets, leading to reinforced mounting brackets. Temperature cycling from -40 degrees Fahrenheit to +130 degrees revealed solder joints that failed under thermal stress, requiring complete redesign of component mounting techniques. By winter 1941 to 1942, the team had prototypes that met the Army's specifications on paper. 3-mile range achieved. Weight under 40 pounds confirmed. Interference immunity demonstrated. Battery life acceptable. But paper specifications meant nothing. The signal. Corps demanded proof. Fort Knox, Kentucky would provide the testing ground. Spring 1942 would provide the verdict. The stakes extended beyond Galvin Manufacturing Corporation's contract hopes. American forces were fighting in the Philippines, preparing for North Africa, planning operations across 2 oceans. Every operation required infantry-artillery coordination. Every coordination failure cost American lives. The SCR-536AM radio had already proven inadequate. If Noble's FM radio failed at Fort Knox, infantry would continue using messenger runners and dying while waiting for artillery support that arrived too late. Noble's team shipped 6 prototype SCR-300 units to Fort Knox in March 1942. The units represented 2 years of engineering work, hundreds of thousands of dollars in development costs, and the lives of soldiers who would either receive radios that worked through interference or continue fighting with radios that failed when needed most. The prototypes worked perfectly in Chicago. Fort Knox would determine if they worked perfectly everywhere else. Spring 1942, Fort Knox, Kentucky. The Armored Force School's testing grounds had witnessed countless equipment demonstrations, new tank designs, improved armor plates, experimental weapons systems. Signal Corps officers had seen manufacturers promise revolutionary capabilities only to watch prototypes fail under realistic conditions. They approached the SCR-300 FM radio demonstration with deep skepticism. Galvin Manufacturing Corporation was an outsider. FM radio was unproven. The Army had invested heavily in AM radio infrastructure. This demonstration would need to be extraordinary. Daniel Noble, Henrik Magnuski, and Bill Vogel arrived at Fort Knox with 6 prototype SCR-300 units, technical documentation, and the knowledge that this demonstration would determine whether American infantry received radios that worked through interference or continued using radios that failed when soldiers needed them most. The testing protocol was straightforward. Prove the radio could communicate at 3 miles minimum range under realistic battlefield conditions. Prove it could survive rough handling. Prove it worked through the electrical interference that rendered AM radios useless. Prove it, or watch the contract go to competitors offering familiar AM technology. The range tests began with conservative distances. Radio operators separated by 1 mile established clear communications, no different than AM radios could achieve under ideal conditions. The Signal Corps observers waited for the distances that would reveal the FM radio's limitations. 2 miles. Still clear. 3 miles, the Army's minimum requirement. Perfect clarity. The observers exchanged glances. AM radios at 3 miles required careful tuning, quiet conditions, and luck. The SCR-300 operators simply pressed the transmit button and talked. Magnuski suggested pushing further. 4 miles. 5 miles. The transmissions remained clear, the FM signal's interference rejection maintaining voice quality that AM radios couldn't match at half the distance. At 8 miles, more than twice the Army's requirement, the radios still communicated with clarity that exceeded AM radio performance at 1 mile in laboratory conditions. The Signal Corps officers who had arrived skeptical were now leaning forward, asking technical questions, requesting repeat demonstrations. But range alone wouldn't prove battlefield worthiness. The real test came when Noble's team positioned running vehicles near the transmitting radio. Jeeps with engines idling, trucks with generators operating. The electrical noise that would render AM radios completely useless. An SCR-536 AM radio, placed in the same environment, produced only static and garbled fragments of words. The SCR-300, operating just feet from the same interference sources, transmitted with perfect clarity. The FM signal simply ignored the electrical noise that destroyed AM transmissions. The durability testing bordered on abuse. Signal Corps testers dropped the radios from truck beds onto hard ground, the kind of handling infantry equipment would receive being thrown from landing craft or hastily repositioned under fire. The backpack frames absorbed impacts. The vacuum tubes, carefully mounted on shock-absorbing brackets, survived. Testers soaked the radios to simulate tropical humidity and river crossings. The moisture-resistant seals held. They operated the radios continuously for hours, testing battery life and thermal performance. The BA-70 batteries delivered their promised 20-plus hours of operation. Tubes generated heat but remained within safe operating temperatures. Colonel Francis L. Ankenbrandt, signal officer who would later evaluate the SCR-300 in combat conditions, watched the Fort Knox demonstrations and understood immediately what the radio represented. This wasn't an incremental improvement over AM technology. This was a fundamental capability gap. American forces would have interference-immune communications while enemy forces struggled with AM limitations. In a war where artillery coordination, air support requests, and tactical coordination determined victory or defeat, the SCR-300 gave American infantry a decisive advantage. One Signal Corps officer, after witnessing the interference immunity demonstration, reportedly said simply, "This thing actually works." In military procurement, where equipment often promised revolutionary capabilities but delivered disappointing performance, those 4 words represented unconditional endorsement. The skepticism had evaporated. The Fort Knox Infantry Board, famous for rejecting overhyped equipment, recommended immediate production. The Army Signal Corps issued production orders in May 1942. Nearly 50,000 SCR-300 units would be manufactured before war's end. The radios would accompany American forces across 2 oceans, through jungles and deserts, onto beaches and into cities. But production approval was just the beginning. Manufacturing 50,000 complex FM radios while fighting a global war required industrial capacity, component supply chains, and quality control that Galvin Manufacturing Corporation would need to build from scratch. The engineering challenge was complete. The manufacturing challenge had just begun. Noble's team had proven FM radio could work on battlefields. Fort Knox validated the technology under realistic conditions. Now came the hardest test, producing thousands of radios per month while maintaining the interference immunity and ruggedness that Fort Knox had demonstrated. Every radio that failed in combat would be a soldier without communications. Every radio that worked would be a life saved. The stakes of mass production were measured in lives, not units. May 1942. The Signal Corps contract authorized production of 50,000 SCR-300 units, more FM radios than existed anywhere in the world combined. Galvin Manufacturing Corporation had built 6 prototypes for Fort Knox testing. Now they needed to manufacture 50,000 complex 18-tube FM radios, while America fought battles across 2 oceans. The engineering challenge was complete. The industrial challenge had barely begun. The production bottleneck started with vacuum tubes. Each SCR-300 required 18 tubes, 6 Type 1T4, 5 Type 1L4, 3 Type 1S5, 2 Type 3A4, 1 Type 1R5, and 1 Type 1A3. 50,000 radios meant 900,000 vacuum tubes that had to meet military specifications for shock resistance, temperature tolerance, and operational reliability. The tubes had to survive being dropped from trucks, soaked in tropical rainstorms, frozen in European winters, and baked in North African deserts. Then they had to work perfectly for hours under combat conditions. Component suppliers across America received military contracts for specialized parts, crystal oscillators for frequency calibration, dynamotors for power conversion, capacitors and resistors rated for extreme temperature ranges, backpack frames engineered to distribute 38 pounds across a soldier's shoulders, antenna sections that could extend to 10 feet 8 inches for maximum range or fold to 33 inches for transport. Every component required inspection, testing, and quality control that maintained the interference immunity Fort Knox had demonstrated. The battery supply chain created its own logistical challenge. Each SCR-300 in the field required regular battery replacement. The BA-70 lasted 20 to 25 hours of continuous use, the BA-80 only 12 to 14 hours. Infantry units operating radios in combat zones needed constant battery resupply. Colonel Ankenbrandt, evaluating the SCR-300 in the Pacific Theater, identified battery supply as the main operational difficulty. The radios worked perfectly. Keeping them powered required supply lines stretching thousands of miles across oceans to remote jungle battlefields. Training became critical. The SCR-536AM handheld radio had been simple: turn it on, adjust volume, press to talk. The SCR-300, despite Noble's team designing it for combat simplicity, required proper antenna deployment, channel selection understanding, and basic maintenance procedures. Signal Corps training programs taught radio operators how to extend antennas for maximum range, how to select clear channels when multiple units operated nearby, how to preserve battery life through proper transmission discipline. The training material emphasized one principle: this radio worked through interference, but only if operators used it correctly. By early 1943, production had reached steady output. Galvin Manufacturing Corporation, soon to rename itself Motorola, led production. Two additional manufacturers, Philco and Dictograph Products, received contracts to expand production capacity. The three manufacturers combined would produce more than 54,000 SCR-300 units before war's end, surpassing the original contract target as demand from combat units increased. The first production SCR-300 units shipped to combat zones in early 1943. The Mediterranean theater received special priority shipments for the invasion of Italy. These radios would see their first combat use coordinating artillery fire and infantry movements in complex terrain, where communication failures had plagued earlier operations. But the Pacific Theater, where jungle terrain and island-hopping campaigns created the most demanding communication challenges, received priority allocation. June 30th, 1943, Bekides City. American forces launched Operation Toenails, the New Georgia campaign in the Solomon Islands. The objective was Munda Point Airfield, a Japanese airbase threatening Allied shipping and air operations. American infantry would advance through dense jungle against fortified Japanese positions. Success required precise artillery coordination. Communication failures would mean American casualties mounting while artillery batteries waited for target coordinates that never arrived clearly. The first SCR-300 units reached New Georgia in August 1943, mid-campaign. Infantry commanders who had spent weeks fighting with inadequate AM radios or messenger runners suddenly had access to interference-immune FM communications. Artillery forward observers strapped on the 38-pound backpacks, extended the antennas, and discovered they could call fire missions through electrical noise that had rendered their SCR-536 radios useless. The theoretical advantages Fort Knox demonstrated in spring 1942 were about to face their final validation: real bullets, real artillery, real soldiers whose lives depended on whether Daniel Noble's forbidden FM radio actually worked under fire. The manufacturing race wasn't finished. Production would continue through 1945, with radios shipping to every American combat theater. But the critical moment had arrived. August 1943, New Georgia. Infantry forward observers with SCR-300 radios faced Japanese positions. The engineering worked. The manufacturing worked. The training worked. Now came the only test that mattered: combat. August 1943, New Georgia. Private First Class Morrison pressed the SCR-300's transmit button. His voice traveled through dense jungle vegetation, past vehicle engines that would have drowned AM radio signals in static, across 3 miles of terrain to artillery batteries waiting for coordinates. The response came back instantly, crystal clear. "Roger, coordinates received. Fire mission acknowledged." Morrison spoke target adjustments. 90 seconds after first transmission, artillery shells impacted Japanese positions 800 yards ahead. The impossible had become routine. The 37th Infantry Division and American Division received the first SCR-300 combat allocations at New Georgia. Artillery forward observers, who had spent weeks frustrated by SCR-536 failures and messenger runner delays, strapped on the 38-pound backpacks and discovered communication capabilities that changed how infantry fought. They could call fire missions through electrical interference. They could coordinate with artillery batteries 3 to 5 miles distant. They could adjust fire in real time, guiding shells onto targets with precision that messenger runners could never achieve. The tactical transformation happened immediately. Infantry units advanced with confidence, knowing artillery support was 90 seconds away, not 10 to 15 minutes away. Japanese defensive positions, dug into jungle terrain and expecting time to reposition between American attacks, found themselves under accurate artillery fire before they could relocate. American casualties decreased as fire support arrived when and where commanders needed it. The communication gap that had killed American soldiers throughout 1942 and early 1943 had closed. Colonel Francis L. Ankenbrandt, signal officer for U.S. Army Forces South Pacific, evaluated the SCR-300's performance across multiple operations. In January 1944, he reported to General Meade, "The SCR-300 sets have now been in action in the Torokina area, Bougainville, in the hands of the 37th and American Divisions, and I have a preliminary report on them indicating that they are exactly what is needed for frontline communication in this theater." His only operational concern was battery supply. Keeping the radios powered in remote jungle locations required supply chains stretching thousands of miles. The radios themselves worked flawlessly. The Mediterranean theater received special priority shipments in 1943 for the invasion of Italy. American forces landing at Salerno and Anzio used SCR-300 radios to coordinate artillery fire and infantry movements in the complex Italian terrain. The radios proved equally effective in European conditions, rocky terrain, mountainous landscapes, and urban environments, as they had in Pacific jungles. FEM's interference immunity worked everywhere. June 6, 1944. Normandy. American infantry waded ashore at Omaha and Utah beaches carrying SCR-300 radios in waterproof bags. Artillery forward observers established communications within minutes of reaching the beach, calling fire missions to offshore naval guns and inland artillery batteries. The radios that had proven themselves in Pacific jungles and Italian mountains now coordinated the largest amphibious invasion in history. Clear communications through the chaos of D-Day, explosions, vehicle engines, electrical equipment operating everywhere, gave American commanders the coordination capability that turned beachhead chaos into organized advance. December 1944. Battle of the Bulge. German forces launched their massive counter-offensive through the Ardennes forest, creating confusion and communication breakdowns across American lines. The SCR-300 became what one general called the single most useful piece of communications equipment employed in the invasion. Infantry units surrounded by German forces maintained contact with friendly units. Artillery observers called fire missions that broke German attacks. Commanders coordinated defensive positions and counterattacks through radios that worked when wire lines were cut and AM radios failed in the winter conditions. The SCR-300 helped turn near disaster into German defeat. By war's end, more than 54,000 SCR-300 units had been manufactured by Galvin Manufacturing Corporation, Philco, and Dictograph Products. The radios served in every American combat theater from 1943 through 1945. Every major operation, Sicily, Salerno, Anzio, Normandy, the Philippines, Iwo Jima, Okinawa, involved SCR-300 radios coordinating artillery fire and infantry movements. Allied forces specifically requested the American FM radios. Japanese and German forces, limited to AM technology throughout the war, never matched the interference-immune communications the SCR-300 provided. The tactical mathematics had reversed completely. In 1940, artillery forward observers faced impossible equations: 1-mile radio range, 3-mile distance to batteries, 15-minute messenger delays. In 1943, with the SCR-300, the equation became simple: press button, speak coordinates, 90 seconds to impact. The forbidden FM technology that the Signal Corps had rejected in 1940 had become the communication standard that gave American infantry decisive advantage in every theater of the war. Daniel Noble's gamble had saved thousands of lives. The war ended in 1945. The SCR-300 remained in U.S. Army service until the mid-1950s, when lighter AN/PRC-8, AN/PRC-9, and AN/PRC-10 Manpack FM radios replaced it. But replacement didn't mean obsolescence. The British military adopted the SCR-300 design in 1947 as the wireless set number 31, making minor modifications for their specific needs. Other Allied nations licensed the design for their own military forces. The radio that had proven itself from New Georgia to Normandy continued serving armies worldwide for decades after American soldiers moved to newer equipment. Daniel Noble received the U.S. Army Certificate of Merit for his work developing the SCR-300. When accepting the award, he said simply, "The development of the walkie-talkie was an academic exercise compared to the contribution of the men on the battlefields, the men fighting the war." Noble understood what engineers often forget: technology serves humans, not the reverse. The 18 vacuum tubes, the frequency modulation circuits, the interference immunity, all of it existed to save soldiers' lives by letting them call artillery support 90 seconds faster. The SCR-300's impact extended far beyond military applications. FM radio, proven under the harshest conditions imaginable combat, gained legitimacy that peacetime demonstrations could never achieve. After the war, commercial FM radio broadcasting expanded rapidly, building on the military validation the SCR-300 had provided. Motorola, the company formed from Galvin Manufacturing Corporation, emerged as a global communications leader. The expertise gained building 54,000 combat radios translated directly into civilian products that shaped post-war America. The tactical doctrine changes proved even more lasting. Before the SCR-300, infantry units advanced cautiously, knowing artillery support required 10 to 15 minutes to coordinate. After the SCR-300, infantry commanders planned operations assuming artillery support was 90 seconds away. That tactical assumption that fire support could be called instantly and accurately became foundational to American military doctrine. Modern infantry still operates under principles established when Daniel Noble's forbidden FM radio proved that interference-immune battlefield communications were possible. The Korean War, beginning in 1950, saw continued SCR-300 use alongside newer radios. The Vietnam War relied on descendants of the SCR-300, lighter, more powerful, but following the same FM principle Noble had championed in 1940. Every subsequent American military radio system, from tactical VHF to modern digital encrypted radios, traces its lineage to the engineering decisions made in Chicago in 1940 and validated at Fort Knox in 1942. The forbidden frequency became the standard frequency. Museums worldwide display SCR-300 radios as artifacts of technological revolution. The Smithsonian Institution preserves units that served in combat. Military museums show the radios alongside the weapons and equipment they supported. Reenactors carefully maintain working SCR-300S, demonstrating for modern audiences how the radios functioned. But the real legacy isn't in museums. It's in every radio that works through interference, every fire mission called in seconds instead of minutes, every soldier who comes home because communications worked when lives depended on it. The mathematics that were impossible in 1940 became routine by 1943. 1-mile radio range became 10 miles. 15-minute artillery delays became 90 seconds. AM radio vulnerability to interference became FM immunity. The Signal Corps experts who rejected FM as unnecessary in 1940 watched it become standard by 1943. Sometimes the best way to win a war is to listen to the engineer who refuses to accept impossible. August 14, 1943. New Georgia, Solomon Islands. Private First Class James Morrison crouched in that jungle with his SCR-300 backpack radio, pressed the transmit button, and spoke coordinates clearly despite nearby vehicle engines and electrical interference. Artillery batteries 3 miles away received his transmission perfectly. 90 seconds later, shells impacted Japanese positions 800 yards ahead. Morrison survived the war. So did thousands of his fellow infantrymen who carried SCR-300 radios from Pacific jungles to European cities. They survived because Daniel Noble believed FM could work when everyone else said it couldn't. They survived because Henrik Magnuski, Marion Bond, Lloyd Morris, and Bill Vogel engineered 18 vacuum tubes into a backpack that could endure combat. They survived because Fort Knox validated the impossible. They survived because Motorola manufactured 54,000 radios while fighting a global war. They survived because one engineer's forbidden frequency became the radio that won the war. The SCR-300 didn't just change how soldiers communicated. It changed what soldiers could accomplish when they communicated clearly. That's the difference between technology and revolution. Technology makes things easier. Revolution makes impossible things real. 90 seconds to artillery impact. That was impossible in 1940. That was routine in 1943. That was revolution.